Good morning. I have 10 a.m., so we will go ahead and get started. So our first speaker is Brian Moberley. He is one of the chief engineers for MBSE at Strategic Technology Consulting. Brian has supported MBSE projects for the DoD as well as the commercial sector, aiding in the development of SysML models for missiles, bomb fuses, satellites, ground vehicles, and more. His engineering curiosity has led him from traditional document-centric systems engineering to helping lead the way in MBSE. He is a veteran of the U.S. Air Force with a Bachelor of Science degree in aviation. He's a commercial pilot, and his experience working in austere environments such as Afghanistan. He is the host of the YouTube channel MBSE Insights. So thanks for being here, Brian.
Thank you.
Over to you.
Thank you. How are you guys? Can you hear me okay back there? Sounds everyone good? All right, awesome. So I appreciate everyone being here. I'm really excited to show you guys all of these different aspects of this simulation model that we developed. It was for a specific program, but this model that you'll be seeing is actually a more generic version of that, so there's no proprietary data in this model. So what I'm hoping that you will take away from this is essentially how you could attempt to do something like this yourself with using Cameo Systems Modeler with Cameo Simulation Toolkit. I know a lot of people, when they talk about dynamic simulations and simulating power, they immediately start thinking about MATLAB and Simulink and doing all of those types of simulations in those environments. And what I'm hoping is that you'll see that it is also possible to do that directly in Cameo Systems Modeler without MATLAB and Simulink, because Cameo Simulation Toolkit does have a robust simulation engine, and it is a both discrete event simulator as well as a continuous simulator. So there, if you go back talking about how simulations actually work with the engines, there are two different types of simulations that can actually be performed, those being continuous or discrete event. And what that really means is how the simulation is doing those calculations and when it's doing those calculations. But what's neat about Sim Toolkit is it actually combines both of those into a hybrid. So it's not simply going from event to event. It can continuously perform calculations and also listen for discrete events in order to update. So that's what you'll see in this simulation. I might go ahead and just jump into a demonstration of this, so that way you kind of have an idea of what we're talking about. But what this is a simulation model of is a hybrid electric vehicle system. And what we've done is actually modeled a very specific solution architecture. So I would consider this more of a physical architecture, but you might consider it more of an analysis architecture. So it somewhat blurs the lines between a physical architecture and a logical architecture. So some of the things you'll see here, you may ask the question, what type of model is this? Well, it's really an analysis model that was done based on a logical architecture on the way moving towards a physical architecture. So that's how this came about, and that's where I would place this in the realm of your life cycle. So this is a very high-level view of the model here. If you notice, there's this block at the very top. I'll try to zoom in on this a little bit for you guys. And we've called that the domain, or the vehicle domain. That could be also considered a system context or a vehicle context. So the naming for that is really not important. I wouldn't want you to get too hung up on whether we're talking about a domain or versus a system context, because really what that's being used to do is essentially encapsulate those three very high-level concepts, which include the operator of this vehicle, the vehicle itself, and then the environment. So a lot of times you'll see environment thrown into block definition diagrams without any more real description of what that means. But what you can see in this example is we've actually added some value properties to that environment, and we'll pull those in for the vehicle dynamics portion to show how that can actually affect a vehicle when we're trying to accelerate to a specific velocity. So if you notice, we have gravitational acceleration. That's something that everyone's very familiar with. But then also air density comes into play when we're talking about drag coefficients and those types of calculations. So notice we also have a rolling resistance coefficient and then the slope of the road. So all of those value properties are encapsulated in that environment block. So just want you to be aware that this this kind of delves a little bit deeper into what you've probably seen on a lot of diagrams that show an environment block, but really nothing more than that, right? So I hope this will help you understand that this is where it leads. When you identify an environment, we're going to actually assign some value properties to that and incorporate those into the parametrics and see how they will affect our vehicle acceleration. So again, this is a very high-level view, but what I'll do now is kind of take a step back, and we're really going to get into the power system for this. So if you notice, this vehicle has a power system, and that was the main focus of this model, was to show how can we model the power system itself, and then how can we simulate that and see that it will actually behave in the way that we would like it to. So this power system is what is decomposed in this model, and I will go over all of the parts of that in a bit. But just so you know, there are various aspects of that, such as a generator, an engine, there's wheel motors involved, there's capacitors, there's a 600-volt bus in this case. So a lot of different things, and we'll step through each of those. But without further ado, I'll go ahead and run a simulation to kind of show you what the whole purpose of this was. And I will do that in a silent mode, and we will talk a little bit about performing simulations with animations on versus running those without animations. So this is a graphical user interface that was developed directly in Cameo using the user interface modeling diagram. And when we play this simulation down here, you will see this all come to life, and then we can track a lot of these value properties that we're interested in. So give it just a second here, and it should kick off. So that is what this looks like when it all comes to life and it's all working properly. If you notice, we have RPMs of an engine that are now coming up, and that's doing that automatically. We'll talk about how we got it to do that automatically. If you notice, there's a battery pack. This is about a Tesla-sized battery pack, 80 kilowatt hour battery. If you notice right now, it's actually charging itself. So you see the state of charge is actually rising. It's doing that automatically with some parametrics and constraints that it has. And then if you notice, there's a bus voltage, and that is a key factor in this simulation, is watching that bus voltage and having things react accordingly depending on what that bus voltage is. So right now, the vehicle is not accelerating, but we can send a sysml signal using this button here and actually cause the vehicle to begin accelerating. And what that did is it actually set some value properties of desired torque and target RPMs of our wheel motors. And this is what actually causes it to begin accelerating. So on this right-hand side, we have the vehicle velocity in blue that is now going up, and then the acceleration is coming down. If you notice, the state of charge of the batteries are now dropping, and the engine RPMs have actually risen now to compensate for that extra power that is needed. So a lot of things happening here. We're going to talk about each of those and how it actually does that and why we wanted to show all of that. One of the main aspects of this, the real goal, was to see how fast we could accelerate to a specific velocity using this power system, and then also verify whether or not that would meet our measure of performance, which was to accelerate to that specific velocity within a certain amount of time. So down here, what you see is it says performing acceleration test, and as soon as this vehicle velocity hits 30 miles per hour, it will then calculate whether or not it meets that measure of performance that we had. And you'll see that in just a moment when we get up to about 13 meters per second. So as you notice down here, it says predicted measure of performance fail, and it highlights that requirement that we had associated with that value property to say, hey, based on all of this, it didn't meet the requirement. But that's really good to know, right? So after doing all of this, we've now determined that if that were our requirement, we were not going to be passing that requirement based on all of these factors. So that is the goal of this simulation. Notice we also have a button here that we can use to stop the vehicle, and that is using the power system without braking. And what you see now is the vehicle is slowing down, and it's calculating the stopping distance for the vehicle as well. So that is always an important factor if you're looking at vehicles, is how fast can you stop, and in what distance can you stop that vehicle. So that is another thing we'll jump into and talk through how that actually happens. But if you notice, when I did that, it actually set that desired torque and RPM back to 0. And then the voltage now shot up, and that's because it's using regenerative braking, so the wheel motors are actually providing a lot of power now back to that bus. So that's why the voltage actually shot back up. So that's the goal. That is what we're going to be talking about, how we accomplished all of this in this model directly using Cameo Systems Modeler with Simulation Toolkit. Also good to note, we did model this in Simulink as well to see if we got similar results. And we were able to get the same results with Cameo Simulation Toolkit as we were in Simulink. So we'll talk a little bit about the delta T and the time step that we're using for this. It is not as granular as what a lot of people would do for a simulation like this, but we found that it was granular enough to provide us the results we wanted. So what I'll do now is flip back over to the presentation and go through some of these slides that highlight some of the pieces of this architecture. So as we mentioned, this is a high-level view. I'll skip this one and go on to the next. And then next to that power system, there are also wheels and a fuel tank that comes into play here because it is a hybrid system. So there's a fuel tank involved. And in this case, it's actually a diesel engine. So we have a diesel engine that's consuming diesel fuel. And we'll talk about some of these value properties. And if you notice, there's some arrays involved here. We'll get into all of the details of why we use some arrays for some of these value properties. But notice there is also, part of this power system is a generator. And this has a direct drive to the engine. So there's no transmission involved. And this architecture is directly connected to the engine. And the purpose of that generator is to provide a three-phase power to an active rectifier module, which is an AC to DC converter, and then provide that power directly to that 600-volt bus. So there is a power controller involved, and the purpose of the power controller is really to set the fuel flow rate for the engine. Inside of that power controller block, we'll look at in a moment, there is a PI control loop that is modeled with an activity diagram. So you'll get to see how we can actually automatically set that fuel flow rate based on the RPMs of the engine as well as the voltage of the bus itself. So really neat how this is done using an activity diagram. So a PI controller is also known as a proportional integral controller. If you've ever worked with control loops, there's also one named a PID controller. This one is specifically a proportional integral controller. So there is an engine involved. In this model, it was based on a 1,000 horsepower diesel engine. So you'll get to see a snapshot of what that engine looks like. But it's actually a 4-cylinder opposing engine that produces 1,000 horsepower. So some very large cylinders involved. And this was for a very large vehicle. So what you'll see are some high numbers that you may not expect if you're dealing with a smaller car or something like that. But this is for more of an industrial sized vehicle. So you'll see some large numbers for things such as mass. Moving on to the battery pack, as I mentioned, there is about a Tesla-sized battery pack in this. And if you notice, there is I believe a baseline for the kilowatt hours that it has. So if there's a value probably hard to see, but the battery capacity in kilowatt hours is 80 kilowatt hours. So that is the battery size that we're dealing with in this model. So there are some arrays involved. And then this bus voltage, or 600-volt bus, is really one of the stars of the show in this model because everything connects to it. So we have things that are providing power to this bus, but also things that are consuming power from the bus. And we can actually we're going to get into how we can show the voltage being affected by either providing power to that bus or consuming power from that bus. An active rectifier in this module, the role that it's playing is that AC to DC converter. So we take that generator that has a 3-phase AC current and actually turn that into a DC current, so direct current, and that's done using this active rectifier module as an AC to DC converter. One thing that you'll notice, and we'll get into in more detail, is the idea of shepherd parameters. That plays a big part in this. This is really the solution architecture for this that causes this model to behave in the way that it does. And what I'm hoping is that you guys will also take away, maybe you want to look more into the idea of shepherd parameters. This was the idea of one of the electrical engineers we worked with, who has done a lot with mobile power systems and dealing with how power is managed in a bus environment like that. So one of these ideas, I'm hoping you'll take away and maybe want to present that to electrical engineers that you might work with and say, hey, this is a really neat idea, really neat way to manage power on a bus. So that is the idea of shepherd parameters, and we'll get into what that means in a bit. So there's the idea of a virtual capacitor in this model, and this is one of the other stars of the show in this model, because this is what actually sets the voltage for the bus in the simulation. So we're calling it a virtual capacitor because in a real system, it would not actually have the capacitance that you're seeing modeled in this system. So if you notice, we have 2.2 farads of capacitance. That is actually a very large amount of capacitance. So that is being considered a virtual capacitor, but it really has to do with the delta T that we're working with and why we're using that large of a capacitor. So it's named a virtual capacitor because it's really there to set the voltage for the simulation. And you'll see how we do that using an activity diagram with some opaque actions and doing a mathematical integration with those opaque actions. So moving along to the wheel motors, there are quite a few number of wheel motors in this system, and we'll also get into why we chose not to use multiplicity to show those wheel motors. In this case, I believe there were 32 wheel motors. Really, it comes down to the computation that the simulation would have to perform if we were to say that it had 32 wheel motors as the multiplicity. So it was a matter of simplifying the simulation. We do have a value property that shows the number of wheel motors, and we use that, but it's a lot easier for the simulation to calculate that once rather than 32 times. So that's why we avoided using the multiplicities of the wheel motors, but there are things that are modeled, such as the power curves and the torque curves of these wheel motors, and we'll get into how that's done as well. Then we have some generic power consumers, and in this case it's an HVAC unit that will be consuming power, but then also a computer module that will be consuming power. And we're going to show how we can prioritize different power consumers on this bus using those shepherd parameters. So if, for instance, we wanted to accelerate all of a sudden, we can actually use the shepherd parameters to say, hey, depending on what your priority was, we may want you to cut off completely and stop consuming power. And in this case, you'll see that that actually does happen with the HVAC unit because it's set to a lower priority. And that's done using those shepherd parameters as well. The mobility controller in this model is really used to set that desired torque and RPM to cause this vehicle to accelerate. And really, we only needed it to have those two value properties, which were the % torque command from the wheel motors as well as the target RPMs. So using those two value properties, we can cause this vehicle to accelerate, and we're encapsulating that in the block called the mobility controller in this model. So here's a quick snapshot of the inside of the generator parametric. That is likely very hard for you guys to see. Does everyone have this on your laptops? And can you see this okay? Otherwise, I can go to the model and zoom in, and we might do that as well. But this is a high-level view of that generator. Generic generator, not the actual one in this model. And during the simulation, it looks somewhat like this in runtime. If you notice up here, we will talk through this portion, which is actually being used to calculate the angular acceleration of the engine based on the moments of inertia of the rotating components. And this is really considered a mathematical integration in order to determine the new velocity based on the acceleration. So we'll get into talking about the constraints and how we calculate that. But there's this essentially a net torque value that we're calculating based on how much current we have flowing through the generator and the actual amount of fuel flow that we have and the torque that's coming in to turn the generator. So a lot of really neat physics aspects to this model that I hope you'll find interesting. So this is the block that we're calling the shepherd parameters, and this is really the star of this model. It's the solution architecture that is really causing all of these different modules that connect to the bus, whether that's power consumers or providers, to behave the way they do. So if you notice, we have a block that's named shepherd parameters, but then there's also a constraint block that has an equation, and it's really an expression that's an if-then-else statement. And what happens is every time the delta t occurs, every time step in this model, that is recalculated for every power consumer. And what it does is it causes those consumers to, I'm going to skip ahead here, to limit their current to following this S-curve. So this is considered an S-curve, looks somewhat like an S, and this is a very desirable way for power consumers and providers to follow this current that they could be limited to based on the bus voltage. So what you see here is actually an output from Cameo Simulation Toolkit that was put into an Excel diagram here to show you what the shape of this looks like. So what we did was essentially, I'm going to change this to a laser pointer. We increased the voltage. This is specifically for one module, but this actually happens for every single power consumer and provider individually. So what you notice here is as we were increasing the voltage from 0 to 1,000 or 0 to 900, the current was limited to following this shape, and that is exactly what we wanted it to do. So that is how we wanted it to behave. And as I mentioned, that is a very desirable way for power consumers and providers to behave in order to keep everything in balance when you're sharing a certain amount of voltage in a power system. So if you notice, this side of the x-axis or y-axis is on the positive side. So anytime that voltage is within this range, we will have something that will have a positive value for current. And what that means is that module will actually be providing power to the bus. However, if, for example, the voltage ends up in this range, that will actually cause that module to begin consuming power, and it will do it at the rate where that intersects this line here. So essentially what we're doing is trying to say that, hey, if you get to the point where there's other things consuming too much of that voltage, it will back off and clamp these devices and cause them to stop consuming power. So that is what the goal is of this whole model. And you'll see how we actually were able to do that for every module that either consumes power or provides power using this shape itself. Now, one thing to note is that this shape can actually change. It's a dynamic shape. So even though it looks exactly like an S right now, depending on some of these values that are dynamic within the simulation, it'll actually shift its shape, which makes it very flexible as well. So I won't go into too much detail on what every aspect of these shepherd parameters are, but they are in this presentation if you're interested. And what each of those 14 parameters do is cause this different parts of this to be affected and have different slopes or different limits. So that's how we can set the current limits and the power limits, is by changing the default values. We're actually using instances in this to say what that specific module should look like when we actually put that into motion. So this is an instance table down here that shows you what that looks like. So these are the 14 parameters, and in this case we only have 5 power consumers and providers in this model, but what we used was an instance table to actually set the values for each of those. So as I mentioned, each of these will be running their own instance of a shepherd parameter block as a reference property, and then by changing those initial values, it causes them to behave in different ways using that exact same expression with that constraint block. So this is a very high-level view of that architecture when it comes to life. So this is an IBD. As I mentioned, one thing that might be hard to see here is we have a DC current. This is for the battery pack itself, and notice it says negative 44 amps. What that means is it is actually consuming power. So that is how it's charging itself, because it happens to be on that left side of the S-curve at the moment in this snapshot. But then there are also some values at the very top that show a positive value for current. And what that means is that module is actually providing power to the bus because it has a positive value for current. So that's how you can know whether or not something's providing current or consuming current, is simply with that positive or negative value for current. Now this is a look into the parametric for the battery pack itself. And one thing to point out here is that even though this value, which was set in that instance table, had an initial value, it is actually going to change dynamically during the simulation using these other constraints that feed into that. So that's what makes this very dynamic. And for the battery pack itself, what was important about this is that it did that based on the state of charge of the battery. So depending on its state of charge, it actually will dynamically change during the simulation to know whether or not it should charge itself or provide power to the bus. Going back to the three-phase generator, I'll show more about this directly in the model, but the purpose of showing this is to say that in order to calculate how fast the engine and the generator are actually turning and accelerating, you typically think of a mathematical equation such as that, which is considered an integration. And it's an integration because it's incorporating the delta t and having to update the velocity every time step. So what's interesting about doing simulations in general is that you cannot actually involve calculus in a simulation. And that's because if you're doing calculus, such as a mathematical integration, you actually have to, you're essentially using an imaginary range of delta t's, right? So you're saying we're approaching this 0 time step, but we need 2 different values. But in a simulation, you only have what is current. So you can't say, unless you look backwards, you can't say what you think it'll be next. So that's where we can use opaque actions to actually hold a value from the last delta t and then incorporate it in, at the next delta t. So that is an opaque action, and what you'll see, I'll do a simulation of this to show what that looks like, but it basically says the angular velocity of this incorporates the current angular acceleration, and that's calculated with a parametric, but then it also takes in the delta t, which is 0.1 in this simulation, and then the new angular velocity. So what happens is it pops that out of that object flow, but then it waits 10 milliseconds using that time event in order to update the next value at the next time step. So that is essentially how you can do a mathematical integration using opaque actions. Now, there's another way to do that purely parametrically, and there's an example in this presentation of how you could do that as well, but there's some advantages and disadvantages of doing that, and that really comes down to whether or not sorry, I lost my train of thought here, but we'll get into the details on that. I do have a slide on that. We'll point out what some of the pros and cons are of using a parametric for actually doing those types of integrations. So, again, we have the virtual capacitor. This is using the exact same concept of a mathematical integration to set the bus voltage, and it looks very similar to the last one that you saw, but in the last diagram, what you saw is that we were actually incorporating to try to figure out what the velocity or the angular velocity was of the generator. In this case, we're talking about updating the bus voltage, but using the exact same idea. So we're updating the bus voltage based on the amount of current that we have on the bus, and then the capacitance value from that virtual capacitor, and then the delta t as well. So that's how we end up getting a bus voltage, is by knowing how much current we have on the bus. And what happens is we see a summation of the negative current values and the positive current values. And then when that's integrated, we'll get that new updated bus voltage at every time step. So that's how we end up getting our bus voltage using that virtual capacitor. Taking a quick step back, a lot of times you want to know, how did we even get to this point in the model? Where did this all begin? Were there logical architectures, use cases, and things like that? What were the stakeholder requirements? So what we've done in this, you may see something looks very similar in the Magic Grid Book of Knowledge for encapsulating measures of performance or measures of effectiveness. And we did the similar thing in here where we said, hey, we're going to capture these measures of performance in a block, and we can actually use those in the simulation to determine whether or not we meet those. So what we did is we said acceleration 0 to 30 miles per hour is a value property, but then we're going to use a satisfy relationship to the requirement that says the vehicle shall accelerate from 0 to 30 miles per hour in less than 8 seconds. Now, what is not actually shown on this is there is a default value for that acceleration value property that is set to 8. It is just not displayed in this. So that's what the model will be using to refer to grab that value to check whether or not we're meeting the requirement, but it's using that value of 8, which means really just 8 seconds. So we're going to see if did we accelerate in less than 8 seconds or did we not? And it's using the default value for that value property to do that and then checking it against that requirement using that requirement satisfy relationship. So at a high level, of course, you could have a use case that would say something such as accelerate the vehicle, and of course our operator would be involved in that. So that's what a high-level use case could be for something like this. And then if you delve into the activity diagram that would actually specify that use case, it would be very simple. It would be something as easy as saying, hey, we want the operator to press the accelerator to accelerate as quickly as possible. And then what happens next? Well, it sets the target RPM and the % torque command. So that's what we were looking at with those value properties in that mobility controller. But this would be the use case that would lead you down the path of getting to where we got for that, right? So it's as easy as saying, hey, we want someone to press an accelerator. But then what happens after that? Oh, the system actually sets its target RPM and % torque command. And that's really what specifies that use case. And this is how we end up actually doing that in what we're calling a physical architecture. And we'll get into the model a little bit to show this. But notice we're using some ALH, or Action Language Helper, in order to access value properties that are not in the context of the activity and the block that's actually executing this. So that's where we incorporate ALH, is anytime we say, hey, this block is executing an activity, but I need a value property that's being held in another block, that's where you can use ALH to actually help you get those values or set those values that are not owned by that same block. So back to the physical architecture, modeling the electric motor and its power. This is a generic power and torque curve diagram, but every wheel motor in a vehicle has specific power curves and torque curves, and you can model those. And what you saw when we ran that simulation is that we're actually following a very specific shape and is dependent upon what we set for these values. So we have max torque and then the slope of that torque, which is a negative value, and then dynamic limit, negative dynamic limit for that, and then a power sink max and a power source max. So as I mentioned, this actually is a wheel motor that can do regenerative braking, so it can not only sink power, but it can source power. So that's where we had to model the limits for how much power it could consume or provide to the bus. And that's what you see modeled with those value properties. Electric wheel motor parametric. So this gets into the details on how we actually caused it to follow those torque curves and power curves. I'll zoom in on that in the model in a bit. But what you see here is some if-then-else Python constraints that are actually taking in those values, such as the limits of the torque and the power, and then running them through a few if-then-else statements, and then outputting some values. And if you notice, one of the outputs of this actually directly feeds into one of those shepherd parameters, which causes that to behave in a certain way in accordance with that S-curve, but it does that dynamically. So even though we have default values set for the wheel motors using these shepherd parameters, those will actually change dynamically, and it's doing that using the power curves and torque curves of this model. This is the other half of that diagram. So it's a large parametric, but this is really just another view. And one of the main outputs of this that we'll get into is that the wheel motors are outputting torque. So that's what you see at the very bottom of this is that there's a little flow property, and it's outputting torque, and it's doing that to the wheels. This is a high-level view of the PI control loop, or the PI controller, that is doing that proportional integral control. And the whole purpose of this activity is to control the fuel flow rate of that engine based on the voltage of the bus. So this is really what makes this whole model work now, is by saying we want this thing to automatically control its engine RPMs, but do that based on the target RPMs and what are voltages of the bus. So this loop that you see, this is a pieced together diagram. That's the top and the bottom of it. But if you put it like that, that loop actually happens at every time step in this simulation. So it actually routes values and starts splitting them out and evaluating them. And the whole purpose is to update the fuel flow rate to the engine based on the voltage of the bus. So that is a really, really interesting concept. Are there any questions so far? I'll just stop here for a moment. If there are, then we'll hand you a microphone.
Thank you first for the presentation. It was very interesting. One question: why did you decide to define the opaque behavior within I would say the activity diagram to compute some performances? I don't remember exactly the slide number because in some cases you can use only a state machine.
Are you saying could we use a state machine to model?
Yeah, the behavior, physical behavior for a current discharge or charge or something like that, and put in place within the state machine or pseudo state an opaque behavior.
You could do that, sure. So what he's asking is if it's possible to use a state machine to drive that opaque behavior?
Yeah, because then using the opaque machine, you can type down the mathematical equation with different formal languages. So my question is, why did you choose to use that more descriptive diagram, which is the activity diagram, rather than simplify it using a state machine that contains an opaque behavior that contains the mathematical equation?
That's a great question. The reason we chose to do that was because it was not responding differently in this case to the same events. So that's where we typically define state-based behavior, is when something responds differently to the same event depending on what state it is in. So in this case, it wasn't responding any differently depending on what state it was in. It was always doing the same calculations. So we essentially didn't need the state machine. We just pulled the opaque behaviors directly out and had them running that loop continuously. So you could absolutely incorporate state machines, and maybe this model would get to the point where you'd actually want to incorporate state machines to say, hey, we want to have maybe some different modes or different states that we could operate in, and then depending on what that mode or state is, set some different values for some of the ways that this behaves, and that's absolutely an option. But at the point that this model's at so far, we didn't need to do that. So great question. But that's definitely an option for some of these things. We were trying to keep it as simple as possible. So.
Yes, but my question is because in control laws theories, they used to speak about the states with different modes for the feedback loops. So that's most of the time how we model such control laws and PIDs with MATLAB. And that's why my question. If then we want to transfer such kind of model into I would say a more robust tool, which is MATLAB for computing, simulating MATLAB for computing control laws, we are more close for the in terms of I would say stereotypes or elements used on the architecture model and on the multiphysics tools. So okay. It's better to use it to transform the elements from one tool to another tool, having the same semantic.
Sure. Okay. Yeah, I think I understand what you're saying. Keep in mind, there are some different definitions of what a state really is out there. So a lot of people, when you're working in tools like MATLAB, Simulink, think of states as different value changes. So if a value is 10 and now it's 11, that is considered a change in the state, right? Whereas when we're talking about sysml states, we're more talking about a sysml state, and in that state, your behaviors can change, right? So there is a little bit of a difference in how we talk about states, but yeah, it would be great to have those ideas converge, I agree. Just keep in mind that when some people say the term states, that may mean something that's slightly different depending on what tools you're working within. So, great question, by the way. I'd love to talk to you more about your ideas on this. Are there any other questions out there? Yeah.
You referenced both doing this model in Simulink and doing it in CATIA. I'd love to know the differentials in time investment and where you see the differential value of those two techniques.
The difference in value between the two tools? Is that what you're saying? So yeah, that's a really, really great question. What he's asking is, what did we glean from doing this in Cameo versus Simulink? How long did it take to model those? And then what was the difference in the value between having it in those different models? So we were actually able to do this faster in Cameo. Some people, it really depends on how comfortable you are, how good of a modeler you are, that type of thing. But we were actually able to do this model in about 5 months. So we stayed pretty close to the same timing for what the guys were working on in Simulink, because we were tossing ideas back and forth for this model, and we developed it together as we worked separately in those different environments. But what we found is having it in Cameo is actually very nice because you can directly correlate all of this back to your requirements in that single source of truth. So of course there are ways to co-simulate these to where you could actually run simulations using Simulink to perform some of those calculations. But that was one of the main advantages for us, was having it all in Cameo and being able to actually tie that directly back to the requirements. Yeah, great question. Does that help answer your question, Bob? Yeah. Okay. All right, any other questions so far?
I'll just have you repeat it. So you mentioned there was a limitation about multiplicity.
Right.
Not using multiplicity. If you have multiplicity in your model, what's the work? Is there a best practice here for simulation if your model already has multiplicity?
Sure, yes, absolutely. So his question is about the multiplicity aspects of this. And as I mentioned earlier, we decided to not use the multiplicity for the number of wheel motors that we have. And the reason was because it was more computationally efficient for the computer to actually do these calculations. Because as you saw with those parametrics, if we were to have a multiplicity, in this case of 32 wheel motors, it would have to do all those calculations 32 more times than it would have had to otherwise. So that was where we decided to simply use a value property and multiply the current in order to act like it was 32 wheel motors rather than having the multiplicity of 32. But then the last part of your question was, if you did have multiplicity, how would you handle that? Is that what you're saying?
Right. If you already have a large model using library models, could you just basically, could you do the same thing with the value property? Or?
You absolutely could. I would say it would probably depend on the model you're using and exactly how many computations your computer's having to perform. You'd probably just want to take it on a case-by-case basis, and that'd probably be the best thing to do. But I would say it just depends a lot, really, on the size of your model. Yeah. Any other questions so far?
Are there any kind of commercial available tool that can do this, or do you have to develop this model by yourself, either in Cameo or Simulink?
Okay, sorry about that. She's asking, is there any commercially available tool that can do this, or do you have to do this in Cameo or Simulink? I'm sure there are other tools out there. This is the one we chose to use. There's a lot of simulation engines out there that can do calculations such as these. As I mentioned, doing it in Cameo, one of the main advantages was to have all of this in our single source of truth and tie those back to the requirements. So that was one of the big advantages of doing this in Cameo. I'm going to get to him really quick first.
Yeah, first I just want to say thank you for all the value you've added to our community via your YouTube channel.
Absolutely.
A lot of great videos on there. It's kind of piggybacking off the Simulink versus Cameo question. What factors would drive you then to maybe do computation outside of Cameo, where maybe the juice isn't worth the squeeze setting it up in Cameo? How do you think about that and that trade-off? Obviously, you're very skilled in this tool and maybe prefer it, but what might actually drive you out of the tool and import results back in?
Yeah, that's a great question. So he's asking, what would cause you to want to incorporate using Simulink or MATLAB or that type of thing? Obviously, there's a lot of libraries of functions out there when you get into using Simulink. So if you maybe don't have time to create functions like these from scratch, or you don't know enough about the functions, that would be a great reason to do that. There are limitations of Sim Toolkit. It's easier to do matrix math in MATLAB and that type of thing. So if you were dealing with matrix math or vectors and things like that, that's when it'd be a great time to really utilize MATLAB and Simulink, because Cameo doesn't do a lot of those complex math type things. But yep, sorry, good. Great question, by the way.
Yeah, a great question, obviously. And to complete that question, I remember at the time, Cameo Simulation Toolkit was able to connect to the MATLAB solvers to compute, especially for the delta T computation, right. Depending on the solvers, Euler solver or other ones, range CUDA and so on. So my question is, I don't see in there in that presentation that maybe it's still on the pipe to be able to connect such solvers and to execute solvers from MATLAB or Simulink and to compute equations solving into the environment of Cameo. Is that still possible?
I'm not quite sure I'm understanding the question. So you're saying, is it possible to co-simulate MATLAB, or what was the last part of it?
Co-simulating MATLAB and Simulink into the using as the orchestrator Cameo for launching the co-simulation and using the solvers of MATLAB.
Yeah, it's definitely possible to do co-simulations. So that is something that is very easy to do, actually, if you wanted to use those constraints and have those modeled as an M file in MATLAB, and you could drag that in directly to a parametric, and then MATLAB will execute that for you. So it's easy to do that. There's a native integration from Cameo, and it is very nice to use if you like having MATLAB perform those calculations. But what we found was we didn't need to have MATLAB involved in this case. So it was a fun exercise to see, what are the limits of Cameo and what can it do? And we found that it was able to do everything that we needed it to do directly without even using MATLAB or Simulink. So great questions. I think we're coming up close to a 10-minute break here. I want to jump in more into the model when we come back, unless there's any questions before we do that. Yes, sorry, one in the back. Are we using a model-based lock?
Clock.
Oh, model-based clock. Sorry, yes, we are using a model-based clock for the simulation time. That's one of the things you'll see on one of the later slides as well. But yeah, absolutely for that, we're using model-based clock. Yep. Great question. All right. Any others? And if not, I say we take a 10-minute break and we'll come back and we'll jump into the model. One of the things I want to get into is basically some of the ideas of continuous flows and how to model some of those things, which you see on here already but may not be aware of. So we'll jump into that when we come back. All right, thanks everyone for coming back. We're going to jump in a little bit about the vehicle dynamics portion of this, and that incorporates the environmental aspects. So what you see here is a high-level view of that vehicle domain. So notice we have this architecture snippet here. It says the vehicle domain, and then within that we have a vehicle and an environment. So that's looking inside of that vehicle domain block with this parametrics. That's what you're looking inside of. And if you notice, over here on this side where it says power system, that entire power system that we modeled that had all those parts is actually all inside of that. And this is a view where you actually see it kind of come out and then start interacting with the environment around it. And what comes out of that is torque. But then notice we also have RPMs going back into that. So interesting that we had to have RPMs going back into that power system. But that was because we really needed that value property in a calculation for the power system. So then we have torque coming out that turns those wheel motors. And then we have a few different equations down here, such as our aero drag forces, our net resistance forces. And then there's this equation here. Oh, tripping again. We have this constraint here that's an equation that simply sums up all of those forces. So we have some that are negative. I think all of the ones that we've modeled in this case act in a negative way, which causes this vehicle to slow down. So we have aerodynamic drag. We have the resistance forces and road slope forces and net linear forces. That all gives us that, and then we put that into the F equals ma equation to determine how fast this vehicle can accelerate. I will jump in to the model in just a little bit, but this is a closer look at that. So what you see coming out, again, is that torque, and that's the whole purpose of those wheel motors, is to produce torque to then turn the wheels. Before we jump into the model, this is a quick look at how you could do a scenario or a simulation scenario within the model using opaque actions. So this is actually an image that was created in Simulink that shows this is a profile that we wanted our, I believe it was the voltage of the bus in this case to follow. But what happened was we ended up saying, all right, we can't do that exact type of profile in Cameo, but what we can do is use opaque actions and just cause it to change a value that would ride that exact same profile. And when it does that, things can react based on that. So that was how we created one of those profiles. And then another way, of course, to do that is what you saw with the graphical user interface, to where you can send signals and have that change value properties for you. So in this case, we sent the signal using the button, and that button simply went to an opaque action that changed the desired torque and percent torque commands. And this is what that looks like in the actual activity diagram. So when we sent that signal, there was an accept event action listening for that signal, and as soon as that happened, this kicked off, which is what essentially updated the RPM target and the percent torque command. And then this is how it actually did that acceleration test to determine whether or not we met the requirement. So I find this to be interesting. We'll jump back into that a little bit in the model so you can see that a little closer. But it was a matter of grabbing the sim time when you hit that button. So it grabbed what the time was in the simulation, set those values, and then it was listening for the velocity to hit those certain marks. So we were checking the velocity, or checking this when the velocity hit 15 miles per hour and 30 miles per hour. And that's what we have the accept event actions with the when on there. So it says when velocity is greater than or equal to, in this case it was in meters per second, so 6.71. Then what we'll do is actually grab the original sim time, what the sim time is now. That's the amount of time that it took, and then it compares that against the requirement and says, did we meet the requirement? So that's how it used the opaque actions to do that. I'll delve in the model and explain a little bit more about how we use the object flows and the control flows to do that too. This is how we calculated stopping distance. So it was a matter of having an accept event action listening for that button, which is the full regenerative braking button. But really all that does is go to the next opaque action that sets the RPM target to 0 and the percent torque command to 0. And that was a matter of seeing if the power system could stop the vehicle without using any mechanical braking, and just see how long would it take or how far would it travel when we set those values to 0. And then there's this little loop here that happens with opaque actions again that says distance traveled equals velocity times delta t. And then it runs that loop, and then it sends that value down to stopping distance equals stopping distance in meters plus the distance we just traveled. Right, so it continues to add those at every time step. So it says in this time step, how far did we go? Add that to how far we've gone. And then every time step, it does that. It continues to add those up until the velocity is 0. And then you know you've stopped. So that's how it calculates the stopping distance. So going into a quick concept here, there is this idea of a continuous object flow, or you can add a stereotype of continuous to an object flow. But what I wanted to point out here is That is good for a descriptive model. And a lot of times if you're modeling logical architectures, you can simply say, hey, we have this object flow, and we want to say that this is a continuous thing that goes from here to here, and that's some type of a continuous thing that happens, so you can stereotype it as continuous, and that indicates that this is something that will be continuous. However, if you go to simulate that, it's not actually going to execute in a continuous fashion because it's only going to send one token across that object flow. So this is where you start getting into the ideas of using value properties to behave in a continuous fashion, and flow properties. And you'll see in a moment how we do that. So that's why I just want to point out it's great to do that if you're creating a descriptive model, not so much if you actually want it to execute. So that's where we start getting into value properties and flow properties. And this is what that looks like. So instead of saying that we have voltage on an object flow going from here to here and mark it as continuous, what we can do is use a value property. So this is the actual way you can model continuous flow in a parametric, and it's essentially by having a value property that has a binding connector to a flow property. So the names of those will match, but in this case there's an interface block that types the proxy ports, and those interface blocks have flow properties. So what you do is use a binding connector between the value properties and the flow properties. I'm sure you've seen some of Salius's videos out there on his MBSE execution channel where he demonstrates this as well. And it's a very nice way to model continuous flow because these value properties hold their value until they're acted on by other types of constraints. So what's interesting though is you can connect that to any other proxy port. This, however, is not a binding connector. This is a connector. And what happens is anytime one of those values change, it simply updates on the other side of that proxy port. So it'll follow that connector path. And let's say you had a few things that were typed as the same thing. What it will then look at is the names of those flow properties. So it first looks to update the same thing with the same type on the other side. And then it'll actually go in and say, if there's multiple things with the same type, then we'll look at the names and know what to update across that connector path. So notice, in this case, something good to note is we have a binding connector between flow properties and a value property. And in this case, we actually had a binding connector directly to a constraint block into a parameter. So that is an option to do as well. You don't necessarily have to bind those flow properties to value properties. You can also bind them directly to another constraint parameter, and it'll simply go right into that constraint and pop out as something else. This is a slide that kind of goes in a little bit of detail on how we modeled that or how we performed that sim time. One thing to note, I won't go too much into detail on this, but we did use arrays in this model, and we did that in order to stabilize the values over a period of time. So for things such as our predicted fuel mileage, we didn't want to have that updating 100 times per second in the simulation. So we said, well, how can we kind of slow that down a little bit and basically smooth it out to where it's not fluctuating as much as all the other values. So what we did is use an array, and we ended up doing a bunch of different simulations and saying for a default, we want to have an array that's just 15 across the board for this velocity array, right? And we did that by running a bunch of simulations and figuring out that really 15 was about the average. So let's just start it out as 15. And then what happens is we then take at every time step, or not every time step, notice this is after 200 milliseconds, which is every time step is 100 milliseconds. So this is about every 20 seconds. We then add a value to the array, and we drop a value off the array. So we incorporate a new value every 2 seconds and drop the one that was the last trailing one at the back end of that array. And we used a little Python script to do that. So notice it says velocity in miles per hour dot append. And that's a way you can actually tack onto an array with Python. So it uses that velocity value, appends it, and then it pops it. So it's called a pop, and it pops that first value in the array. So that was what that was in order to basically update it with one value every 2 seconds, but then drop that value that happened 2 seconds ago. And it averages that out then using a parametric. So notice over there, it has a parametric that simply does a mean function of that entire array. So when it does that, you get a nice stable value that's not fluctuating as often as the time step of the simulation. And this is the model-based clock that we use. So by default, you don't use the model-based clock when you run simulations. It's another type of a clock that runs with the engine, but it is not as accurate. So in order to use the model-based clock, you go into your simulation configurations, and there's this one value, the start time. So notice it says start time equals 0. You put that in there, and that actually enables the model-based clock by setting start time to 0. You could start it at a different point. There's no real reason why you'd want to do that, but it's good to know that that's how you can actually use the model-based clock, is by setting that start time to 0. And then what you do is actually set the time steps for this. So in this case, we used a step delay of 100 and a step size of 100 in milliseconds. And what that did is actually make it seem like it actually took that long for it to go that time step. So that's what the step delay was. Notice this is the other way to do a mathematical integration parametrically. And as you saw before, we could use opaque actions to do that, but this is actually a more efficient way to do it computationally. But wanting to point out here that this can actually cause some unsolvable recursive loops in your model if you have things that are outputting something here and then getting taken into another mathematical integration. Cameo can run into some unsolvable loops parametrically because it'll keep updating both sides of that, right? So that's one of the disadvantages of using a parametric to do mathematical integrations, is you can run into some recursive loops, which is why we ended up simply using opaque actions, even though it's a little bit more computationally expensive for your computer to do that. As far as making this model better, one of the things we wanted to do is go through and try to get rid of magic numbers. That was a term we came up with in this project to say magic numbers are numbers that are in these equations and no one knows what they mean, right? So in this case, you see an example, multiplying something by 8. Why did we do that, right? So that would be better off as a value property. That way everyone knows what that is. So that's one of the ways you can go through and make your model better. Is if you've put in numbers that no one knows what they mean, go back and make those value properties. That way everyone knows what they mean. And then this is the idea of why we chose not to use multiplicity, is essentially because we'd have to do 30 times the amount of computations for this model. Some acknowledgments here before we jump into the model. Frank Jones, he was one of the guys that was the electrical engineer. He had the idea of the whole Shepherd parameters. Shepherd is actually a name of a person from back in the 60s, I believe, who came up with this idea of Shepherd parameters and actually managing current using those. So he was the one that was the driving force behind this. Also, Mike Skoke, Steve Miller, Chris Lamb, and Alex Whittier, who we have in here and spoke yesterday. I'm going to jump directly into the model now, but I may stop for a moment and ask if there's any new questions since the last time we had questions.
So for the model-based clock, are you just changing the sim config to have like start times and the step size and stuff, or is there like actually a block in your simulation that is like has a master time parameter that is being incremented?
That is a great question. We were simply updating it in the sim config, but that was an idea of a way to improve this model that I've had as well, is to essentially say, let's create some variable that we could change across the board if we wanted to change the time step and only have to change it in one place and have it proliferate throughout the model. So that would be a great idea. That's not what we did in this case, but that would be a great way to make this better for sure.
Thanks.
Yep. Let's see. I want to run a few simulations, but then also talk through some of the things that you're seeing in this. So, So let's start here in this generator. I find this fascinating how it's actually updating its velocity, so the rate that this generator is turning at, and how we actually calculated that. So let's take a closer look at that. I'm going to run this simulation with animations on so you can actually see these in action as well. So this is some of the physics for a generator. The whole purpose of the generator is to output a voltage, but what is interesting about this is you can actually determine how that generator is affected by the amount of current that is flowing through it. And now I say through it and not being provided by it, because if you ever look at the internals of a generator, there is what is called a rotor and a stator. The stator is the outer portion of that, and the rotor is actually turning, and there's a way that that current actually does flow through that rotor in order to produce an electromagnetic current. So we actually have this value property that is called current, but notice it is flowing into the generator, and that is a pattern you see throughout this model that if you didn't know why we did that, it might seem a bit strange, because typically you want to say that, hey, this is providing current, so let's send current out, right? But in this model, what we did is actually model the effects of the current by taking current in. So when this runs, I'll go ahead and push play here. What you'll notice is that current is actually coming into the generator because we want to see how that affects the generator. And if you've ever used a skill saw with a generator possibly, or ever ran anything off of a small generator, what you'll notice is anytime you draw current, you'll hear those RPMs dip down. You hear it go, right? And that is actually what we can show it do in this model. And it's because it actually puts a counter torque on the generator. And you can model exactly how much counter torque that is using a few equations. So notice the current comes in and then is ingested into one of these equations. Where's that going? There it is. So that current that is coming in is ingested into this equation here, and notice it says torque equals 30 times pi times the square root of 3 times the constant electromotive force times the current, right? So using that exact equation, you can determine how much counter torque is being applied by drawing that much current through your generator. And then what you do with that is send that to another equation. So notice it says the electromagnetic counter torque is now this specific amount in Newton meters, right? So that is the amount of torque that is pushing against the generator due to us drawing current through the generator. But what we can do with that is create this net torque equation, because as you know, we have an engine that is actually trying to increase the velocity of this generator, right? So we know how much torque we have coming from the engine. We'll get into that down here. But then when we do a net torque, so we add up the amount of negative torque, which is the counter torque, and the amount of positive torque, we know the net torque. And then what we can do with that net torque is actually pull it into this equation that says angular acceleration equals net torque divided by the moment of inertia, right? So that is a physics equation. Well, how do you get moment of inertia? Well, we actually got it from the vendor, right? So you could calculate what that moment of inertia is by using some other equations, but if you already know it, why not just put it in the model? At one point, we had some equations in here that calculated the moment of inertia, but we said, hey, if we already know what it is, we don't need to calculate it every time step. Let's just say what it is, right? So that's what these value properties are here, are basically we're saying the amount of moment of inertia of the rotating components of the engine is this. Let's add that to the amount of moment of inertia of the rotating components of the generator. And now we have this combined moment of inertia. And what that does is act in opposition, and it spits out the angular acceleration at every time step. So then you incorporate that in with the velocity that's currently going using this integration, and now you know how much the generator is actually increasing or decreasing based on how much torque is coming from the engine, how much counter torque is being caused by drawing current, and now you know the exact velocity that that generator is turning at. And when you know the velocity, you know the voltage. So that is the main output of this, is to say, hey, what is the voltage coming out of our generator? Because that voltage is then going over to that AC to DC converter to be converted to, in this case, a 600 volt DC. So that's what you see happening here are the outputs of the generator, and then this is what it's doing to convert that AC current to a DC current. And this incorporates the idea of Shepherd parameters as well. So notice there's an instance of the Shepherd parameter block here, and that is outputting a DC current. This is affecting one of its Shepherd parameters dynamically to know how much power it is actually providing. So the output of all of that is now we have a DC current that goes down to our DC bus. So this is the DC bus where everything converges. We have power consumers, power providers, and as we noted earlier, a negative current means there's something drawing current, or if something has a positive value for current, it's providing current to the bus. So notice that's what these values are here. We have a positive value for current. That's one of these. And I deleted some of the lines on here. So you may not see what they're all being connected to, but that's coming in from all of these proxy ports that have some of those flow properties hidden, is where we have all of that current that's converging at the bus. And that is how each of these know what to do in accordance with that bus voltage. So notice down here, these are our power consumers. They have the exact same pattern. They're using different instances of that Shepherd parameters block to know what their current should be based on the bus voltage. So we have, this one says bus voltage is 592. This is the exact same thing, 592. But notice their current is different. And it's different because they have different values set for the Shepherd parameters. So now they know how to behave using different instances of that exact same block. And one of these is consuming power. I think both of these are consuming power at the moment. If we go over and look at the battery, notice we have this state of charge that is being calculated. One of the things I didn't jump into, there's an activity that is also draining that battery based on how much power we're using. So there are some conversions that are happening here in this battery. Based on the amount of current, we know how much power we're using in kilowatts, and then over time we can determine how much that's depleting the state of charge of the battery, which of course is then affecting its Shepherd parameter dynamically. So that's what's happening inside of the battery at that point. Any questions on any of this so far? I don't want to bore you guys. I find this stuff fascinating, but
just
yeah.
one small one. I don't think I need the mic. You've said you've done a lot of things to reduce the computational burden here.
Right.
What's your memory allocation down there on this current running sim, and just what kind of hardware you got running?
That's a great question. So as far as how much memory it's using, I have a 64 gigabyte RAM laptop. It actually has it'll boost its GPU up to, I think, 5.4 gigahertz. So it's a little bit of a beefy laptop. Right now this is 43,000 of, 6,000 of 8,000 being used, but I have it set to a max of 40,000 gigs of RAM, or 40 gigs of RAM, 40,000 megabytes, not 40,000 gigs. That'd be a lot of RAM. Yeah, so that's a great question. Yeah, but what we have found is even on some of the other laptops we've ran this simulation on, they're able to handle it as well. So I think we've ran this on a laptop that has 16 gigs of RAM, and it was able to do it as well. So, what is interesting is at every time step, Cameo is storing every value property, so it does take a toll on the RAM after a while, because at some points in this, you may want to export all that data out of your simulation, so Cameo has to store it. That way you can actually export that if you wanted to. So it does start racking up a lot of RAM usage. Any lingering questions out there? I want to jump over and look at the engine here for a moment. This is something I actually left out of the slides. It was not intentional. But basically, I want to go into this engine and how that's calculating torque, and then look a little bit closer at that PI control loop. So let's do that. I'll go ahead and run the simulation with animations again. So notice there's a few proxy ports here. There's a desired fuel flow rate that is coming in as a result of the PI control loop. That is what's down here. And that goes up to this value property. This is actually a not necessary constraint that we did. So notice it says current fuel flow rate equals desired fuel flow rate. That was unnecessary. We could have simply routed this directly over to this equation. But this is an interesting constraint. So we have fuel flow rate going into this constraint, and it's actually pulling in the RPMs of that engine and generator also. And then out of that, we're getting mechanical power. So notice we have the mechanical power is produced by knowing the fuel flow rate and then multiplying it by a few numbers that look like magic numbers, but they're really there as constants and a way to convert some things from kilowatts and to watts and things like that. So that's what the multiplying fuel flow rate by 18,000, subtracting the RPMs and multiplying that by 18. That was a matter of doing a few conversions, but we did it with magic numbers. That would be better if we use value properties and explain that a little bit more, but that's what that is. Notice that out of that we have mechanical power that goes directly into this equation that outputs the torque. But it does that knowing the RPMs as well. So when you know the RPMs, you can convert that to the radians per second by using a simple equation of pi times 2 times RPMs divided by 60, right? So that produces how fast the generator is turning in radians per second, which you can then take into this equation as well. We threw in an if then else statement. I think that was for purposes of getting close to 0, so we didn't have some weird things happening with 0 values. But that's why we have an if then else statement. But the simple equation is that rotor mechanical torque, which is what we wanted to find out, was simply produced by knowing the amount of mechanical power coming from here and dividing that by the radians per second that it's turning at. So out of that, you get the amount of torque coming out of that generator. And then that was what was going up to the generator to then calculate the angular accelerations of all that. So that is how we ended up producing that. Getting down here to the PI control loop, as I mentioned, this entire loop happens at every time step, and its whole purpose is to really cause the fuel flow rate to come up, but in a nice stable fashion. Let me show you what that looks like in the graphical user interface. When I run this in a silent mode, so we won't see the animations in the diagram, but you'll see all of this here. And the result of that activity diagram will be this right here, right? So a little bit of wobbliness there. This is somewhat interesting, but when I pause that, notice this red line right here. That was actually the rotation of that generator. And when this started out, we had some immediate power consumers that caused this voltage to drop. But that was the result of the counter torque placed on that, was that the RPMs of the engine actually dropped due to that drawing of power. So that's what you see is that dip right there. But then the blue line is the target RPM that was calculated with a parametric. And then the red line is the actual RPMs coming up to that slowly as the result of that PI control loop, saying, hey, we know what the target RPMs are immediately. We can calculate that. But we don't actually want it to come up to that immediately because that would maybe put too much strain on the engine. Or it could cause you to, in this case, foul glow plugs because they're not spark plugs in a diesel generator or diesel engine. They're glow plugs, so you wouldn't want to dump too much fuel into that engine too quickly. So what you can do to mitigate that is use that PI control loop that then causes the actual RPMs to slowly come up to that target RPM. And that's what that activity diagram is doing. That was the purpose of that PI controller. So that was what we really wanted to happen there, and that's what's causing this to behave in an automatic way, is by using that activity diagram to say, at every time step, let's look at what the target is, and then slowly bring that up. let's see, any questions on any of that? Okay. So what I'll do now is actually slow down this PI controller a little bit so you can see what some of that looks like as it's going through there. So it's just flashing right now because it's at max speed, but if I were to slow it down, what you'll see is those are the object flows passing through there. And as I mentioned, this entire loop happens at every delta t, every time step of this simulation. So right now we see a lot of 0 values that are being passed through it. There's some trues and falses popping out of some of these opaque actions. And then notice after the time step, it loops back around. It's going to do that exact same thing. And that's what's causing it to come up to that desired RPM nice and slowly. So I find that very, very fascinating. I don't know about you guys, but I think that was a really, really neat thing to do in Cameo, is actually model that PI controller and watch how it could behave automatically in that fashion. So, one other thing, let's jump over to, as I mentioned with the directions of the proxy ports on some of these, I think that's a really important thing I don't want to leave out. Is the direction of the current and the voltage of all of these power consumers and providers. So notice again here we have, this is one of our power consumers, and then the direction for the current is actually always out, right? And then the direction for the voltage is always in. So as I mentioned, that was because we needed to know the effects of the current, not exactly modeling the actual flow of current, but more so modeling the effects of the current. So that's why you see on all of these power consumers, we're always taking in voltage, looking at that, and then we're outputting either a positive voltage or negative voltage, and then sending that up to that bus so then it can produce a new voltage when it's integrated in with that virtual capacitor. So that is a pattern you see throughout this model. But keep in mind, we did not model the actual current. We just modeled the effects of the current. And that's why you see all of these directions that seem kind of strange, but it's because we needed to know how much current it is coming into that virtual capacitor to then turn that around into a new voltage. So that is really one of the main concepts behind what causes this to work properly. If there's anything specific you guys want to look at, I'll leave it up to you guys. Right now, there's a few directions we can go. We don't have a whole lot of time left. We could look at some of these if-then-else Python constraints that model the power and torque curves, but I'll kind of leave it up to you guys if there's anyone who's really interested in seeing a certain aspect of this with the time we have left. This could be incorporated into a digital twin for sure, yeah. That's a great question.
So is the model available online?
We're not currently sharing this model, even though it's a generic version of another model. We're unfortunately not sharing with the general public. Now that said, there are all the slides, and there's a video that I have on my YouTube channel that actually is about an hour or so long that goes in depth on the entire model. So all those details are out there, but we'll leave it up to you guys to try to recreate it. Or you can come talk to us. Great question. Any other questions?
So when you were modeling the generator engine combo, I kept thinking of using something like Modelica for that, because they have such an extensive library of components that all the properties
Sure.
there.
Okay.
Did you look at a Dimola Modelica slant to some of the physics-based components?
It's a great question. So he's asking, did we look at Modelica or Dimola as an option for some of the libraries that are available? And we did not in this case. We had the advantage of having some really smart SMEs that knew a lot of these equations, and we're like, hey, here's the physics functions, so let's model these. And we didn't need to do that, but that would be a great option as a way to improve the model, even to look at some of those options. So yeah, great question. Was there another?
So I have two questions. In slide number 44, you use SimTime1 as a object flow. Why is that?
That's a great question. He noted where we have a SimTime1 used in that opaque action. Let's flip over to looking at that for a second. So I did say I was going to come back to this, so great time to come back to it. We did this because this is the portion where we actually check whether or not it meets the requirement. So notice you can call out in opaque action SimTime. It'll immediately grab whatever the SimTime is, right? However, we needed to hold that value and then 8 seconds later grab a new SimTime and then see what the time difference was in SimTime, right? So we needed to know, let's say the SimTime was 14 seconds, and then all of a sudden, when it gets up to velocity, it's now 21 seconds. We needed to do the math on that and say 21 minus 14 has now passed. So in order to do that, we converted the object flow, the name that it comes into this opaque action, we called it SimTime1, because if we would have left it being called SimTime, it would have used the new SimTime, right? So we actually wanted to use the old SimTime, so we had to convert the name of it to something else. That way, when we get into the equation here, you can see this. When it grabs SimTime right here, that's the new SimTime, while SimTime1 was actually the old SimTime. So that was the initial that we converted to being called SimTime1. So it's what it is now minus what it was before, divided by 1,000. That way we convert that to seconds. And then that's how we ended up getting that delta T, essentially.
Okay. So that tells me I need to update my glasses. I didn't see that. Okay. The second question is, you mentioned in the parametric diagram you removed some connections, but the values are still changing. What do you mean by removing the connections? In the parametric diagram, there you say that you have hidden the connections or removed the connections, but still on the proxy ports the values are changing. And I didn't follow, like, what do you mean by
I think I know what you're talking about. So,
hide or remove?
Great question. So he's talking about how in that parametric you didn't see some of the binding connectors at that bus, but they are there. So right here, notice you don't quite see where these values are coming from because we've hidden the what's inside of these just to make it a little cleaner diagram. But let's say I want to display those flow ports. Now you actually see what it's connecting to here, right? So it was just eliding what was on the diagram. Even though it's still there in the model, it's still happening in the model. You're not seeing it directly connected, but it's still there. Yeah. Sorry, was there another question? Okay, great. Great questions, by the way, guys. If there are no other questions, I'll go ahead and let you guys go. But I could keep going on this for a long time. So maybe if some of you want to come up and talk afterwards. Otherwise, I really appreciate your time.